Welcome back, engineers. You're tuned into the Foundry by Forge College. I'm absolutely thrilled to be your guide today as we tackle one of the most critical, high-speed components of Solana's architecture. We're going to jump right into this explainer and unpack what the Turbine protocol actually is and exactly why it matters so much to this network's completely insane throughput.
So, picture this scenario. A block leader has just produced a massive 10 megabyte block. Okay, now you need to send that data to 100 different validators literally instantly. If you try to push that massive load all at once, you're going to completely choke the network's bandwidth, right? But Sealevel, which is Solana's parallel execution engine, has incredibly strict latency requirements. It's constantly hungry, and it needs that data right now to keep processing transactions. So how do we solve this delivery dilemma?
Here's our engineering blueprint for today. We'll start with the block delivery dilemma, introduce a stagecoach relay metaphor to make sense of the mechanics, and then break down the core actions: fragment, fanout, and reassemble. Finally, we'll tune the turbine knobs and tie it all together in the complete data pipeline.
All right, Section 1, the block delivery dilemma and the fundamental problem with moving massive blocks.
Enter Turbine. This is Solana's dedicated data delivery subsystem. Its entire reason for existing is to minimize block propagation latency right after a block is produced. Think about it. If a leader tries to send a monolithic 10 megabyte blob sequentially to every single validator, execution slots are inevitably going to stall. Back pressure builds up and the whole chain just slows to a crawl. Turbine solves this gracefully by fragmenting the payload into smaller packets and broadcasting them through what we call a fanout distribution.
Moving to Section 2, the stagecoach relay metaphor. To really visualize how this fanout works in practice, we need to talk about breaking down the heavy wagon.
Think about the traditional heavy wagon approach. It's like loading all 10 megabytes of block data into one giant, creaky wooden wagon and trying to force it through a really narrow mountain pass. It's incredibly slow, it completely overloads the path, and if it hits a bump, the whole supply chain stops dead. Contrast that with Turbine's approach, the stagecoach relay. We break that massive cargo into small, easily manageable parcels. We hand them off to a network of local stagecoaches who then pass them down to local couriers. It's agile, it's parallel, and frankly, it keeps our heavy wagon totally out of the mud.
This metaphor actually maps perfectly to the network code. The original depot is our block leader. The parcels we're packing are the data fragments. The stagecoaches carrying them are the intermediate peers in the network, and those local couriers making the final delivery, those are our downstream validators. Once this mental model clicks securely into place, the entire architecture becomes so much more intuitive.
Section 3, fragment, fanout, and reassemble. Let's see how this metaphor translates into the actual engineering mechanics.
This right here is the absolute heart of the system, broken down into 3 distinct steps. Step 1, fragment. We partition the payload, but we don't just chop it up blindly. We attach sequence identifiers and cryptographic checksums so every single piece is verifiable upon receipt. Step 2, distribute. We push these fragments into a fan-out tree of intermediate peers, our stagecoaches. And Step 3, reassemble. Downstream validators check the checksums and rebuild the original block. The really crucial point is that this fragmentation, combined with a fan-out tree, creates a massive parallel pipeline where no single connection is ever overwhelmed.
Let's look at a concrete number here, 10,240. If we take our 10 megabyte block and chop it into tiny 1,024 byte pieces, we instantly get roughly 10,240 highly manageable fragments. So instead of one agonizingly slow 10 megabyte transfer, we suddenly have over 10,000 tiny packets flying across the network simultaneously. This simple math is a real game changer. It allows the network to maximize everyone's bandwidth in parallel.
Okay, Section 4, tuning the turbine knobs, because Turbine isn't just some rigid structure.
As you'll discover when exploring the advanced learning programs at Forge College, world-class engineering gives operators actual, tangible dials they can turn to adapt to changing network conditions. Look at this blueprint. Fragment size controls parallelism. Smaller means more parallel transfers, but it does raise the CPU overhead to process all those headers. Fanout degree is how many primary peers the leader initially sends to. A higher fanout saves the leader's uplink bandwidth but increases total network broadcasts. Redundancy overlap shoots extra fragments out into the network to prevent packet loss, and the repaired timeout dictates how fast a node asks for a missing piece. Every single tweak here directly impacts network performance.
But hey, things in the real world go wrong. What happens when a stagecoach peer decides to take a mid-delivery nap?
Well, Turbine is built specifically for these exact failure modes. It handles reordering and partial deliveries effortlessly because of those sequence IDs we mentioned earlier. And if a piece is truly missing, a validator doesn't bother the main block leader. It just sends a local repair request to its closest neighbor. It's a constant balancing act of redundancy versus CPU waste, but it successfully keeps the main depot entirely stress-free.
Section 5. The complete data pipeline. Let's bring it all home by combining Gulfstream and Turbine. If you joined us for the previous Capstone Build Explainer, you remember Gulfstream. Look at how these two pair up. Gulfstream operates in the pre-block phase. It pre-sorts transactions and pushes them to leaders to minimize mempool friction. Turbine, on the other hand, operates in the post-block phase. It takes that sealed block and literally shatters it into a million pieces for rapid network delivery. Together, they form two perfectly complementary halves of Solana's data pipeline. Basically, Gulfstream lines the data up and Turbine knocks it down.
If you take nothing else away today, I want you to remember this exact quote from the explainer. Fragmentize to parallelize, fan out to distribute load, and local repair to limit tail latency. These three core principles are the absolute lifeblood of Turbine. They are exactly what keeps Sealevel's parallel execution engine constantly, relentlessly fed with data.
Which leaves us with one very provocative question. With transactions perfectly pre-sorted by Gulfstream and sealed blocks flying at stagecoach relay speed across the Turbine network, what is actually happening inside that Sealevel execution engine? Well, to find out, you're going to have to join us for our next explainer. Keep feeding that curiosity and be sure to visit forge.college to continue your Web3 learning journey and dive deeper into these incredible architectures. I'll see you in the next one.